Just think about that for a second. Here's how I was able to take over your account in ChatGTP. That's a real quote from a security researcher this year. It wasn't some theoretical threat, it was a real working attack. And it all boils down to a fundamental part of the internet that we all use every single day, but barely ever think about. What we're diving into today is web cache poisoning. You can think of it as this invisible threat that lurks just beneath the surface of the web. It takes one of the internet's best features, its speed, and twists it into a seriously powerful weapon for attackers. And that's the big question, right? How on earth can something built to make your favorite sites load in a snap be turned around to steal your data or hijack your accounts? Well, to understand the crime, you first have to understand the unwitting accomplice in this whole digital heist. And the consequences here are genuinely shocking. I mean, we're not talking about small glitches. We're talking about complete account takeovers on massive platforms like ChatGPT. Researchers have even used these same techniques to compromise the login pages for services like PayPal. The stakes really couldn't be any higher. So let's meet that unsuspecting accomplice I mentioned. It's something you interact with literally every time you browse the web, but you probably don't even know it's there. We're talking about the web cache. Okay, so think of a web cache like a super efficient librarian. They know which books are the most popular, so they keep a few copies right at the front desk. That way, instead of running to the back of the library every single time, they can just hand one over instantly. On the web, these caches are often huge services called content delivery networks, or CDNs, and they are absolutely essential for keeping the internet feeling fast. And here's how it's supposed to work, in a perfect world. The very first time you visit a site, the cache doesn't have a copy. That's a cache miss. So it goes and grabs the page from the main server, saves a copy for later, and then sends it to you. But for every single person who comes after you, it's a cache hit. They get that page instantly from the cache. It's faster for you, it's less work for the server, everybody wins. Or do they? This is where things get a little dark. See, the attacker's secret weapon isn't some fancy, complicated malware. Nope. It's all about exploiting the simple rules that these caches use to decide what to remember. It's about finding the cracks in the system. Now, this is the really critical part to understand. The cache doesn't look at the entire request your browser sends. It's lazy. It only focuses on a couple of specific things called the cache key, usually just the website's name and the path of the page you want. Everything else, like all these special HTTP headers you see here, are what we call unkeyed. The cache just completely ignores them. But, and this is a big but, the web server in the back, it might pay a lot of attention to them. And that mismatch, that's the dangerous blind spot. This slide shows the problem perfectly. It's a classic case of what security folks call parser confusion. A researcher found this on Glassdoor. They sent a cleverly crafted URL. The cache, the CDN, saw one thing, it cleaned up the URL and thought it was just a safe, normal page request. But the server in the back, it interpreted it completely differently and saw a request for a vulnerable page that should never ever be cached. It's this disagreement that an attacker can use to their advantage. So once an attacker finds one of these cracks, they can start the heist. They can use that confusion, that disagreement between the cache and the server to cause all kinds of trouble. And these attacks usually come in two main flavors. First, you've got web cache poisoning. This is all about tricking the cache into storing your malicious stuff, say a nasty script, and then serving it up to every poor soul who visits the page after you. Then there's web cache deception, which is almost more clever. You trick the cache into storing and then revealing someone else's private data, like the contents of their personal account page. So let's see how this all connects in a real attack chain. First, an attacker tricks a victim into clicking a special link. Notice it ends in .js. That simple trick fools the cache into thinking it's a harmless file, so it saves the response, which is actually the victim's private account page, full of sensitive info, like a security token. Now the attacker can just go and grab that cached page and steal the token. With the token in hand, they trick the victim one more time, getting them to click a link that uses that stolen token to, say, change their shipping address on a shopping site. 2 clicks, and the victim's stuff is now on its way to the attacker. And please, don't think this is just some niche problem for a few random websites. This is a big deal. This table, which comes from GitHub's own security lab, shows this exact kind of vulnerability in the systems that developers use every day. When major repositories like NPM and Docker Registry are vulnerable, it means the entire software supply chain is at risk. You could poison software right at its source. So this brings us to the really tough part. Why is this so persistent? Why is it so hard to fix? Well, it's because this is a never-ending battle, and it's being fought in the complicated, interconnected layers that make up the modern web. If you want to know just how serious this is, just follow the money. Companies are paying out some serious cash in bug bounties for this stuff. PayPal paid out almost $40,000 for 2 related cache flaws. GitHub paid over $7,000 for another one. These numbers tell you everything you need to know about how badly these companies want these vulnerabilities found and fixed. But fixing it isn't always straightforward. This timeline shows a really interesting dispute with Next.js, a huge web framework. A researcher finds a flaw. The Next.js team says, nope, that's not our bug. It's a problem with how the CDN is configured. But then they quietly push a commit that looks a lot like a fix. This whole situation just begs the question, in today's complex web, who's actually responsible when something breaks? Is it the framework, the cache provider, or the developer who glued it all together? And that, right there, is the heart of the problem. The modern web isn't one thing. It's a long chain of different systems from different companies, CDNs, load balancers, servers, and each one speaks a slightly different dialect of the internet's language. All an attacker needs to do is find one spot in that chain where things get lost in translation. That's where the vulnerability appears, and that's how you can poison the memory of the web itself. It's a strange paradox, isn't it? We built this amazing distributed memory for the web to make everything faster and more efficient, but in doing so, we also made it fragile. It's a shared resource that's open to being tampered with. And that leaves us with a really tough, lingering question. If the web's own memory can be poisoned, what can we really trust online?